asked me to give this talk here. I still remember the days when I walked into ISI to be interviewed by Kalyan Sinha and KRP. I mean, I just took a train and went. They said 15th August, you have to be here before this. So I landed at 2 o'clock on 15th August and I was ready at 5 o'clock. I went to their office, they both started laughing and said, come the next day. So the ISI days were tremendously exciting because I went there as a physics student completely clueless about mathematics, and I was plunged into KRP's lectures. At that time, Sundar joined, and he also dragged me into lectures on finite algebras. So I was one of those students who was first introduced to finite algebras by Sundar when he was learning the subject himself. So it was a tremendously exciting experience to be clueless about mathematics but still get intuition about so many things that happen there. Since then, Sundar and I have moved almost closely through various institutions. When I went to the US, he was also there. We used to meet often. When I came back here, I used to go to Bangalore from here. And then finally, we managed to get him here. And I cannot believe that he's becoming old. That says something about myself. That's why I cannot believe it. Okay, anyway, it's great to be here. So I thought that this talk, I'll generally talk about the area that I work in rather than a specific problem that I've solved. So here goes. I was just now arguing with Gadadhar that, we have forgotten how to write without realizing that I would have actually preferred to write it on the board than use this technology. Okay, so the area that I work in is special theory of random operators of physical interest. So what one does is takes a probability space, usual. I will keep myself to the d-dimensional lattice. So I will think of this as a group and then think of this group acting on omega, and that action I'll call T. And then I'll take this Hilbert space L2 of ZD and define this discrete Laplacian, which is given by taking the sum over the function on the neighboring sides. Usually one has a difference here so that it becomes a discrete derivative, f of x minus f of x minus epsilon over epsilon or whatever. So since the distance between points is 1, that epsilon is just 1, so if you subtract, that is a derivative, and that's why it's called a discrete Laplacian. But one drops all that for spectral theory and just considers this operator. So just take the sum of the operator acting on a function is sum of nearest neighbors. And this is a self-adjoint operator, and using Fourier series, one can find out that its spectrum is actually from in the interval equal to the interval minus 2d to 2d, and that is purely absolutely continuous spectrum there. So all these factors one can easily get. And then along with this, one takes a multiplication operator valued random variable q on this probability space omega. I want that multiplication operator to come from a sequence of real values, so that for a given path omega in omega, the associated operator q omega is given by multiplying by this sequence q omega of n. And those are real numbers. So and as n varies here and omega varies here. Remember, I have started with the probability space, so there is a probability measure here, and based on the choice of the probability measure, you get various different models. One usually takes some connection between this action and the operator that I'm going to define here. The operators that I'm going to consider are just sum of these two operators. And because I have taken this sequence omega to come from a space which I'll give you in a moment, I'll consider in this talk these operators to be bounded. So I have a family of bounded self-adjoint operators on L2 of ZD, and these self-adjoint operators, as the parameter varies, I require that there is some kind of a covariance condition. If I take U to be the translations on L2 of Z, the L2 of ZD by ZD itself, that is, take a function here, translate it, that action is called UN, translating by a point M. So that action on L2 of ZD and the action of ZD on omega are related via this relation. That's called covariance. That is, if you shift functions on LD and look at the associated unitarily transformed multiplication operator Q omega, then that is same as shifting the point and looking at the associated operator there. And this covariance also translates to a covariance of this family of operators of the similar type, because these translations commute with delta and they are constants. So as far as omega are concerned, they are constants. Otherwise, the UNs commute here. Therefore, the same kind of covariance also translates for the covariance of these self-adjoint operators. So therefore, what I have is a probability space with ZD action there, L2 of ZD, and a family of, a measurable family of, measurable in an appropriate sense, a measurable family of self-adjoint operators which are covariant in this sense. So I can move either on L2 of ZD by unitary translations, or move in the probability space via this action to another point in the orbit. So this is the grand model. These collections of operators are used to model crystals and the dynamics there of a particular electron, one electron in a crystal. So let me go to a specific case. Let me take, for simplicity, -1 to 1 to the ZD to be my probability space, to be my sample space, and then Q omega to be multiplication by the sequence omega of n. Omega is a point there which is a sequence. Just take that and multiply. Therefore, these omega n's take values from -1 to 1. As n varies, you get this sequence. It is clear that these give automatically bounded operators by the virtue of the fact that I have taken -1 to 1 to be the set of values that omega takes. So here, different kinds of choices of probability measures P will tell you different things. So for example, periodic crystals are those when your probability measure is supported on the orbit of one periodic function, taking values here. So take any periodic sequence taking values there. So, and look at the orbit. The orbit is a finite set of points in this space, and look at the atomic measure there. If you want, you can make it invariant and so on, and that is precisely P. So when omega is here, the points are just translates of phi. Finitely many translates, because it's a periodic sequence, it can only take finitely many values. So that's called a periodic crystal. In other words, you take a crystal, imagine the atoms of the crystal to be located at the point of ZD, and think of the potential as those which repeat periodically. So finitely many distinct atoms periodically located. So that is one model. And the second model, another model, the so-called quasi-crystals. The quasi-crystals are very differently stated in different contexts. So in this context, we can say a quasi-crystal is one where this P is supported on the orbit of finitely many periodic functions. However, they all have mutually incommensurate periods, so linearly independent periods. Therefore, what happens is that this resulting sum, of course I can also multiply by different weights, but simply let me take this sum. This sum of functions is not going to be a periodic function on the lattice, but it is called a quasi-periodic one, because there are finitely many frequencies. So this object in the physical literature is called a quasi-crystal, However, the way the quasi-crystal is talked about in physical literature is as if you take a crystal and take an irrational hyperplane and then project it and so on. So this is a reformulation of that in terms of, because all you're doing is handling countable sets and talking about nearest neighbor hoppings and interactions and so on. So the model, the physical model that you can model quasi-crystals is precisely this. So an electron moving in a quasi-crystal is modeled by this Hamiltonian. And of course, going beyond this, you have almost periodic crystals, namely when P is supported on the orbit of an almost periodic function, where you take alpha j's to be positive numbers adding up to 1, L1, and then you take periodic functions of incommensurate periods. What you get is an almost periodic function.
The action is the obvious better reaction, right?
Yeah, yeah. Usual action of shift. That is the usual action there. T is the action set. So just shift them, and then under that, however, this function, the shifts, if you take the closure of the shifts in the uniform topology is compact, not pointwise topology. Okay? So the topologies change with the context. So this is an almost periodic function in the Bohr sense if you take an appropriate topology, closure in the appropriate topology. And then you can keep proceeding like this. So this is the most regular, that is in the crystal you periodically translate, everything is beautiful, and then a little wild, more wild, and the wildest case is where from one side to the another you cannot compare the potential. So you have, the wildest case is P is a product measure coming from this being IID random variables with some common distribution. So at a given site n, you take a random variable distributed as mu, another site you take an independent random variable but same distribution and so on. That is the wildest case. Then you cannot compare there is no relation between the potential from one site to the another. That is the most wild case. So this entire collection of things are formulated as these are the objects of interest in studying disordered systems in the mathematical framework. So you have this disordered system modeled as the potential being orderly or non-orderly and so on. And in that, one electron is moving, and the dynamics of that electron is governed by this Hamiltonian that I have written down, h omega delta plus q omega, and that is the object of interest. That's a self-adjoint operator for each omega. So the first question that we are interested in is, what is its spectrum? What is the spectrum of this family? As omega varies, the operators change. So what do you mean by spectrum? Does the spectrum change, or what happens? So that is one question. So to give a feeling for why this question is important, imagine, so you have a crystal, so you have your computer, you have a semiconductor which is just a crystal, and suppose you interchange the potential at two different locations, and suppose the whole spectral features change, then you find that you cannot manufacture anything at all with those things. Because if the spectrum is going to depend where you're going to be having transport or non-transport, depends on how your potential is changing from point to point, then you cannot have any material at all. You cannot have any computers. You can't be doing anything. So you must have some order there. That is why one is interested. As omega varies, is there some kind of order among all these operators? That is one question. Second, a question of interest, both in physics and in mathematics, is that what is the Lebesgue decomposition of the spectrum? Lebesgue decomposition means that, as we know, given a self-adjoint operator, even one, you have a spectral measure associated with it, so that a measure class you have associated with it uniquely. And this measure class gives rise to numerical measures when you pick up different vectors. So numerical measures have a Lebesgue decomposition in terms of splitting them absolutely continuous with respect to the Lebesgue measure, or singular with respect to it, or atomic, and so on. So this is the Lebesgue decomposition one talks about. And when you do the Lebesgue decomposition, the totality of the supports of the Lebesgue components is called the different types of spectrum. That is called Lebesgue decomposition of the spectrum. The spectrum at a point, then what is the statistics of these eigenvalues, as what is the distribution of those eigenvalues, that is the local statistics, that is of heat rest. And the spectral theory of these collections of operators also have other offshoots, which I will mention towards the end. Not necessarily, the offshoots are not in spectral theory, but in something else. So let's put a little bit more structure. Till now I have not assumed anything on P other than the fact that it's a probability measure. So let me now assume that under this action this is an invariant measure and it is also ergodic, so that we don't worry about other ergodic decompositions and such. So once you have that, then the spectra of all these operators is an invariant set almost every omega. That is, there's a fixed set such that the spectrum, this collection of sets agrees with it almost every omega, and so does the absolutely continuous spectrum, singular continuous spectrum, and point spectrum. Okay? These sets are identified, as I said, via the Lebesgue decomposition of numerical measures associated with the spectral measures of the self-adjoint operator. So once we put the ergodicity condition, then all these sets get fixed. By the way, this talk I'm trying to give, I'm not giving any credits, none of this is my work. Maybe a little bit at some point may be mine, but I just want that clear. I don't want to mention names because I want to give a feeling for the subject rather than anything else. So the questions, while it is relatively easier to identify what this set is, identifying these things or if they are present and so on is a little harder question, is sometimes much harder. So in the case where my operators come from IID random variables with some common distribution mu, and in one dimension, or if the variance of this measure is large, variance is nothing but these are all measures on the real line. Mu is a measure on R, or -1 to 1. Actually, the way I have chosen it, mu is a measure on -1 to 1, that interval. So its variance is nothing but integral of x squared d mu x. I'll assume that the mean is 0. Okay? So that is the variance. So either in one dimension, or if the variance is large, large is relative, one has to give a quantitative thing which occurs in the theorem, but let us say for this talk large is something that is large, then the continuous part of the spectrum, which is the union of these two sets, is empty. That means these two components are missing, only this is available. In any dimension, provided variance is large, or in one dimension. Any other spectral type, when the variance is small in higher dimension, is still a conjecture. Nothing else is known. Not only nothing else is known, nobody even has any clue as to how to approach this problem. For periodic potentials, that is the periodic P, the spectrum looks like a union of finitely many intervals. So it's something like this. This is what is called bands. It is for this reason that when you listen to a physics talk most of the time, they keep talking about bands and gaps and so on. These are the bands, these are the gaps. And they also put the spectrum vertically. So if you want to translate, if you ever go to a physics talk in quantum matter physics, you do this vertically and then think of this as the band and think of this as the gap. It is nothing but the spectrum. And it is, you can associate with, for these operators, this part of the spectrum is purely absolutely continuous. So you can associate certain kind of behavior of the Fourier transform associated with this, and that's why it is stated that you have some transport there. So the electrons sitting with these energies are supposed to be transported, are capable of carrying electricity, and with these energies, if they are there, they don't conduct. So that is why you will find materials which are both conducting and insulating and so on, semiconductors. So these models explain certain features of semiconductors also as physical models. So in one dimension there is one particular model, one particular class of potentials that is very challenging. In fact, it took a long time to figure out the spectrum, and that is called the, sorry?
Rational or irrational alpha?
For almost all, that is Lebesgue measure. Okay. So I consider this potential, take a number lambda, cosine of alpha n plus theta. Of course, when alpha is rational, this is a periodic function. It just falls in the earlier class, so it's not interesting. The spectrum is just bands. So the interesting case is only when alpha is irrational. So in the probability space, you just parameterize the orbit by a parameter theta, you can put it, and lambda is in 0 to infinity. So this collection of potentials give rise to what is called a almost Mathieu operator. This is a potential coming from reducing a magnetic potential from 2 dimensions, but that we will not go into. So anyway, the spectral theory of these operators with delta plus this is of, it was very hard to show. And finally, the results that are available now is that for almost all alpha and theta, with respect to the Lebesgue measure, the spectrum is given by this. H theta is nothing but delta plus this. Delta is the discrete Laplacian, remember. When lambda is smaller than 2, it is purely absolutely continuous. There is no singular spectrum at all. And lambda is bigger than 2, this pure point spectrum. In fact, the theorem, the way it is proved, they show that if there is pure point spectrum for lambda bigger than alpha, bigger than 2, then there is purely AC spectrum for lambda smaller than 2, if and only if. It is that kind of duality that is shown. It's quite hard. And then for lambda equal to 2, the spectrum is purely singular continuous. And it is also shown recently, I'm meaning maybe 6-7 years ago, that it is also nowhere dense set for almost every irrational frequency alpha. That this statement was called the 10 Martini problem, because mark cards were supposed to have given offer 10 Martinis for whoever solved this.
Would you
So,
put 2 pi also?
2 pi where? Here? Yeah, you can put a 2 pi.
Yeah.
Right.
Otherwise, rational, irrational.
Exactly. Yeah. So alpha is irrational modulo 2 pi. Okay. Put it 2 pi. Of course, irrational means modulo 2 pi. Yeah. So this problem was
The first case you said is absolutely continuous.
yeah.
How is that compared to low and dense?
It's a nowhere dense absolutely continuous set. You have nowhere dense sets of positive Lebesgue measure. In fact, if you take the unit interval, you have nowhere dense sets which have full Lebesgue measure. Okay? So it is that kind of set. So it's wild in every sense somehow, even though it's a simple almost periodic function. The spectrum is pretty wild. So that's why it kept so many people busy, and they were all excited. So in the case when, even though in higher dimensions you don't have much of a result, if you slightly modify in dimensions bigger than or equal to 2, if you consider these independent random variables with the variance decaying at infinity with some rate, then you have a mixed spectrum. You also have purely absolutely continuous spectrum here, and then purely point spectrum in the complement, if that is possible. So as it is stated, when QNs have bounded support, the distributions of Q have bounded support, then this part of it is not possible because the operator has essential spectrum here. However, you can also extend it to the case where the distribution of the single Q has infinite support. It is for that case that this component is present. You can show that. There are cases where you can show that when mu is support is R, then R minus this set is really point spectrum there. So there is the dichotomy you can exhibit, but with this additional condition. So even to extend this beyond a rate that is shown, that is available now, is still not feasible. So this is as far as the spectrum and spectral structure of these operators is concerned. The one is interested in the Lebesgue decomposition of various operators. And of course, there are various techniques that you use to show all these things. Now let me go to what is called local statistics, the second problem, which is that, so if you take a point in the point spectrum, so we know now that when you take independent random variables as your model, then for that case, H omega coming from independent random variables, then you take a point in the point spectrum. What you do now is that you take a box lambda L centered at 0, side length 12 plus 1. Box means box of the lattice of points of that distance. Consider the orthogonal projection onto that box in L2 of ZD. Truncate this operator with that projection. And what you obtain is some operator, you can think of it as a matrix. So you can think of it as a finite dimensional matrix. A matrix of dimension 12 plus 1 cross 12 plus 1 to the D. So call that HL of omega. So it's a finite matrix indexed by, parameterized by L. L is a natural number, side length of the box. Then this collection of operators, in view of the fact that we have taken independent random variables as potentials as omega varies, it will actually turn out that all its eigenvalues, you can put them in an order, increasing order, whatever, are all simple. If they are not simple, count them with multiplicity and label them. There are so many of them because the dimension of this matrix is this. There are so many eigenvalues. They are all random variables, real random variables. Because this is a Hermitian matrix, these are all real numbers, the eigenvalues. So those are random variables. So take these eigenvalues and then take an eigenvalue and shift it by alpha so that you center the eigenvalues at alpha. Alpha coming from the spectrum of this, fix some energy there. And then scale it. So take an energy in the spectrum of H omega, look at this finite dimensional matrix, look at its eigenvalues, center them there, and then blow it up by a factor 12 plus 1 to the D. Blow it up by a factor which is the volume of this box. This is the factor. Okay? What happens is that typically, if you look at the spectrum of these numbers, typically they are all spaced around 1 over this volume. That is typically the case. So when you blow it up, you are roughly bringing them close to distance 1. That's what you are trying to do. Okay? That is why the scaling. So then what you get is actually a point process, a process that takes values, discrete values. And not only that, you actually have a a family of point processes. So this is not a process, sorry, I take that back. These are a bunch of random variables. Now what you do is look at the atomic measures supported at these numbers, the Dirac measures. So each of them is a measure, Dirac measure supported at this point, so it's a random measure. Add them up, that gives you a atomic measure, random atomic measure associated with this matrix. And in fact, as L varies, you get a sequence of random atomic measures. Okay? So this is a point process. You get a sequence of point processes. Another way of looking at it is that you take the spectral measure of HL, this matrix, translated by alpha times the identity matrix of the same dimension, scale it with this factor, look at the associated Hermitian matrix, look at the spectral measure of that, take the trace, that gives you a numerical measure, and that measure is precisely this, random measure. So you can do it in two different ways. That is precisely what you are doing here. So take this sequence of random measures and see if this sequence of random measures, something happens to it in the limit. And if so, what is the behavior? So the statistics is the following. So suppose QNs are IID random variables which have uniformly beta Holder continuous. What does it mean? You take the measure mu, that's a measure, take any interval of length epsilon, okay? Take the measure of that interval. If that behaves like epsilon to the power beta as epsilon goes to 0, then, and uniformly irrespective of where you have chosen the interval, you call it, the measure is beta Holder continuous, okay? Your measure is continuous, not only that, its distribution function is Holder continuous with exponent beta. That's what it means. So take IID random variables whose distribution is Holder continuous with exponent beta. That's what it is. And then take a number here in the spectrum of the H omegas and put a technical condition. So what you do is you take this operator, look at the resolvent for a point in the upper half plane, take the inverse, that's a bounded operator, take the matrix elements, this is a bounded operator on L2 of ZD, so you can think of it as a matrix with respect to the standard basis. Look at the matrix entries, njth entry, nmth entry, take the average, now that's a random variable because this is a number, complex valued number, it's a complex number, complex valued random variable. So take the absolute value raised to power this and take the expectation. This is a bounded random variable, so taking the power and taking the average are all finite because we are integrating with respect to, this average is integrating with respect to a probability measure. So it's a finite quantity. But as m varies, we don't know how it behaves, so you require that is summable. Actually, this condition is shown whenever you show that you have this set. That is how it is shown. Therefore, there are cases where this condition is satisfied. And then, as real z varies here, take the sup over imaginary z of this collection of numbers. This collection of numbers now only varies with z, so you take the sup. And suppose that is finite. Alpha doesn't occur here. It doesn't matter. It's actually independent of alpha. The reason why it's independent of alpha is because of this condition. Okay, it doesn't matter. That alpha will come later. So put this condition, then the statement is that this point processes, the sequence of random measures that we have constructed converge to a Poisson random measure in the vague sense with intensity given by this quantity where L is the Lebesgue measure. And what is this quantity? This quantity is related to the original operator as follows. You take the original operator and look at the spectral measure of that and take its average. That average, sorry, I should have put it here, the matrix entries with respect to the standard basis element supported at 0. This is not operator, I should put it here 0, 0, okay? That is missing there. So you take this numerical measure n, that's actually absolutely continuous, take its derivative at alpha, at that point alpha, right? So that is the number n alpha here. And this derivative exists almost every alpha, therefore this statement is valid almost every alpha with respect to the Lebesgue measure. So this sequence of point processes converges to a Poisson random measure with this intensity. That is the local statistics. That is, in other words, if you somehow take this point spectrum of the operators, blow it up sufficiently, then what happens is that the collection of eigenvalues, if you blow it up sufficiently so that they are all at roughly positive distance, then if you look at it locally, then those points are Poisson distributed. That's what it is. 5 minutes. 5 minutes, oh God. Poisson distribution means this. Firstly, for disjoint intervals, these two random variables are independent. And this is a random measure, remember. So random measure of the interval to be k, the probability goes like this. This is the intensity. Okay?